Hey, okay, we're going to take a look at this trig question, and we're going to graph it, and we're going to model it with a function. So it's a few bits of key information we should be aware of as we get started. So first of all, the radian whipper has a diameter of 6 meters. So I'm assuming it's round, and if its diameter is 6 meters, let's just draw a picture of this. Is basically a Ferris wheel question, but it sort of goes underground, or it's like not very tall, and I guess they have to climb up some platform to get on it, right, to jump on board. To its max height is where they're going to start. But what it's basically saying is that its diameter is 6 meters, right? So the distance from its max to its min is 6 meters, which is very similar to another feature that we're used to hearing about when we're talking about trig functions. Half the distance from the max to the min height is going to tell us the amplitude. So the 6 meters is twice the amplitude. So we already know A is 6 over 2, which is 3. All right. It gets on at the max height of 7.5 meters. So 7.5 meters is where they're going to start. So our max equals 7.5 meters. This also tells us, because we know the diameter, so if this point here is 7.5 meters above the ground, then this point down here is 1.5 meters above the ground. So we can find the midpoint, like when it's roughly in the middle, and that's going to tell us our axis of the curve, or sinusoidal axis. And so when we do that, we can say that's our min right there. And so our sinusoidal axis is, or our C value in our equation, is going to be the midpoint between these two. We find that by taking 7.5 plus 1.5 and dividing it by 2, which is 4.5 meters above the ground. All right, so we've got quite a few features already. We've got the amplitude, we've got that C value, the one that's added on at the very end. Let's take a look at what else we've got. So it's unfortunate that it says the max height of 7.5 meters is where they start at time is equal to 0. That's because over here, it tells us this, we're going to model it with a sine function. So there's different language that we have to be very aware of. And so I don't know if this question was abbreviated in any way, but if it said sinusoidal function, that means we have our choice as to which to use, cos or sine. If it says a sine function, we must use sine. And that's the unfortunate part, because something that starts at the max and is heading downwards to start, that models cosine perfectly. Since we're going to have to use sine, means we're going to have to do a phase shift to adjust for that starting position, which is not the end of the world. It's just an extra step. That's all. They do makes 10 complete rotations in 60 seconds, which means it does one rotation per 6 seconds. So one rotation per 6 seconds. All right, and that's our period right there. That's the period. So if we're going to model it using the following function, I'll show you which pieces we already have. We've got f at, wait, it's a height, right? So the height, h, at time t is equal to our a value, which we already know, times the sine function itself. And inside there, we're going to have that k value, which we'll figure out using the 6. It is not 6. It's 2 pi over 6, but we'll come back to it. T, not x. T minus d, which is our phase shift, plus c. Okay, so that's what we're going to do. So we already have A, it's 3. We already have C, it's that midpoint we just found. This is 4.5. Let's find K. So K is going to be equal to 2 pi over the period, which is 2 pi over 6, which reduces to pi over 3. Okay. What else do we have here? So the only thing we're actually missing now, because this guy here is C, this guy here is A, this guy here is K, so we've A, K, and C. So all we're missing is the phase shift. So spoiler alert, the offset between a sine function and cosine function is always going to be half the period. So we could use that information. Now, I find it difficult to visualize that. So I am going to graph this first and then come back to that feature, and then we'll finish up the function afterwards. So the graphing is easy because we just go based on the information here, right? Just wants us to graph one full rotation, right? Sketch a graph showing one full rotation. And so means we start at 7.5 meters above the ground. There's our start point, which means after one full period, we're going to end there as well. Right? So there's our end point already. Our min value here, we've already determined is 1.5. That's where it's going to hit and turn around. And halfway between those two is 4.5. So let's just make that nice little dotted line that goes all the way across. We have to remember that one full cycle is 6 seconds, which means let's do the halfways. So halfway is going to be 3. Halfway there is going to be 1.5. Not the prettiest distribution of time, but it's okay, it'll work. And halfway between those two is 4.5. So now that we've broken these down into what we might call quarter points, so it's 1, 2, 3, and 4 sections to our graph, we know it's going to complete this symmetrically, which means if we're starting up here, it's going to be a quarter point until we hit the axis of the curve. It's going to be another quarter point before we hit the minimum, another quarter point before we're back at the axis, and another quarter point till we're back up at the max. So there's our rough sketch. It is. Try and make it as curvy as possible. Lovely. So now we have options in terms of how we can model this with a sine function. If we remember the behaviors of a sine function versus a cosine function, right? So if this is a quick model of a sine function, we can see that it starts on the axis of the curve heading upwards. So that's the behavior we're looking for, right? That's for just y equals sine x. For the upside down version of that, something like that, we're on the axis of the curve heading down. So that's y equals negative sine x. And that's handy for us here because we can actually see that's happening right over here at the 1.5 curve. So what we can do is we can make a negative and then say it's been all shifted to the right by 1.5 units. So that will work. Again, cosine, as we know, starts at the max going down, and we could flip it over for negative cosine starting at the min going up. The other thing we could extrapolate is that this goes back, and again, another distance the same as this, quarter point, 1.5 seconds, and that could be our start point. So we could also say this is a sine function, just it has been shifted to the left by 1.5 units, and it came up, and now it's going to continue. So we have a couple options. I'll give you 2 answers for this one because the phase shift is essentially like a little bit open. And again, if this was sinusoidal function, we could have just done a straight up cosine function and not have to deal with phase shift at all. All the rest of the features are legit though. Okay, so we can see here, we can say here, this is 1.5 right, or we could say 1.5 left. And so as a result, we get that h at t is going to be equal to, let's do the one to the left first, because then it's not negative. I don't know if that really matters, but whatevs. So we've got -3, right? So it's a negative sign. Oh, I guess I'm doing the one where we shift to the right first. Sine of k, which is pi over 3, t, and we flipped it over, so we're going to the right. So if it's gone to the right, that means there's going to be a minus here by 1.5. You could write that as 3 over 2 if you like. I've never met anyone that prefers fractions except my own weird self, plus c at the end, which is 4.5. Alternately, we could also say h at t is equal to +3 times the sine of pi over 3 t plus 1.5, right? Because that's the 1.5 to the left, plus 4.5. Okay, so there's our graph of one cycle. There are 2 possible equations. And again, if it was a sinusoidal function, we could say 3 cosine pi over 3t, did not need this at all, plus 4.5 at the end. And that makes things way easier in this particular situation. Okay, so I hope that helps. And that's all I got for this one. Have a great day.